Hi, this is Dr. John Bergduff. In this video, we're going to explore exponential growth and decay. So what we're going to find out is that many real-world situations can be modeled by equations that are exponential in form. The graph that represents that real-world situation looks like an exponential function. And you might remember that those are very common to see where you have an upward swing like this or a downward swing like that. Some examples include population growth. Population, for example, will often double more over on regular intervals. Every time it doubles, the growth is much larger. Radioactive decay also follows the pattern of an exponential function, but that's one where the function is decreasing instead of increasing. There are lots of examples. And in the next few videos, you're going to see several of those practical examples and what they look like. In this video, what I want to do is show you just the general form for what a function would look like that models exponential growth or decay, and show you just some of the mechanics of how to work with the mathematics involved. So I'm going to change my screen here and give you a definition and also show you an example. Exponential growth and decay. So the general form for an equation that models exponential growth and decay is this one right here. And you can see it's an exponential function, particularly using that value e that's so mysterious that we've seen many times. In this formula, the y0 or y sub 0 represents the initial value of a quantity that's experiencing exponential growth and decay. If we're talking about the population of a country, this might be some specific beginning date on which we take a census, and then we watch how it grows from that date. The y0 would actually be the population on that date, and the 0 refers to that's our 0 year. Similarly with radioactive decay, that could represent an initial amount. The k in the formula is a unique constant. That's going to be different for every equation that we look at, and often it's the thing that we actually need to use real-world data to calculate. T is time, that's up here in the exponent with the k, and that's generally in years, although maybe not necessarily always, but generally in years. And y represents the value of that quantity, whatever it is, after t years. So again, in this video, we're simply going to look at some mechanics where, given that we have a function that fits this form, how do we solve for one thing or another? So let's suppose that we know what y0 is. That would represent the initial value of whatever this quantity represents. We have a value for time, and we have a value for the quantity after that many years. The thing that would be unknown in this case is that constant. And that's going to be a critical thing in many applications to figure out what that constant is. So this will just talk about the mechanics of how that's done. First of all, let's just substitute into the equation. Looking at the general equation itself, the first thing we would have is the y value. So that's 37,413. Maybe that's a population, I don't know. Next, we would have the y0, so that would be the 36,000, like that. E is literally that constant E, that 2.718 that your calculator knows how to do. K we don't know, so we'll leave that as an unknown. That's up here in the exponent. And then we also have a 7 up there. So this is what the equation would look like. Now, let's talk about how we will solve that. So the best thing you want to do first is to see if you can get the exponential factor by itself first. And the way to do that would be to divide both sides. I'll just turn that into a division bar. Divide both sides by that constant 36,000. Whatever you do on one side of the equation, as long as you do it on the other, you're good. And I'm actually not going to figure that out separately. My calculator is going to handle all that for me. For the time being, I want to leave it as it is. So we will have 37,413 over 36,000. On the other side, the constant 36,000 divides out just like that. And you'd have e to the, and if you will excuse me to do this, let's say instead of e to the k times 7, let's say e to the 7 times k. Looks a little bit more familiar. So the variable I'm trying to solve for is up in the exponent. I need to somehow liberate that. Well, we've seen this with some more, just abstract questions. To liberate a variable out of the exponent, the best thing to do is to take a logarithm of both sides. That can be logarithm base anything, but it makes sense to choose a logarithm that your calculator can do. That would either be a natural logarithm or a common logarithm. Because my base over here happens to be e, the thing that makes the most sense to do is to take a natural logarithm of both sides, because that's a logarithm base e. And then to remember this very important formula that we've seen before, that if you have the logarithm base a of something raised to the power at the same base raised to the x power, because the logarithmic function and the exponential function are inverses of one another, that gives you nothing more than the x, the exponent. So over here on the right, when I say the natural log of e to the 7k, that's just going to be 7k. So it'll look just like this. The natural log of 37,413 over 36,000 equals, and then the natural log of e to the 7k is just 7k. That's that inverse function relationship. And then you can see that to get the k by itself completely, you'd have to divide both sides by 7. Now that looks a little bit icky on the left, but that's all right. Let me just reverse the two sides here so that we're figuring out that the value of k is the natural log. Maybe it'd be useful to put the 37,413 over 36,000 over 7. And that's the calculation that I've got to do. Now, let's talk about doing that on the calculator. You do not have to do this in little bits, like figure out what this fraction is and write that down, and then take a natural log and write that down, and then divide by 7 and write that down. Your calculator will do everything. Let me show you. So I'm going to need to switch cameras back, and then I'm going to need to share my screen. And you will see here in front of you, let me move myself out of the way a little bit here. You'll see that I've written over here in this document exactly the calculation we need to do, and I want to show you how to do it on the graphing calculator. First of all, there is only one factor in the numerator, so you don't necessarily have to put parentheses around the entire numerator. You can go ahead and start your natural logarithm, but you do need the parentheses here that will represent that you're taking 37,413 divided by 36,000, close parentheses. That's everything in the numerator. And then one more division, divide by 7, and hit enter. And this gives me the value of k. Now, most of the time, there'll be some sort of instruction that tells you that they want that rounded off to a certain number of places. Let's say we want to round that off to 4 decimal places. If I do that, then my value for k, actually let me put k over here. My value for k is going to be 0.0055. Now again, in future videos, we're going to see exactly some lovely applications of how to employ exponential growth in decay. But this is just to kind of get us familiar with the mechanics of the mathematics. So I hope that is good. And we're going to stop right